The lock-free queue implementation provides a thread-safe mechanism for inter-process communication without explicit mutual exclusion primitives. The queue maintains two atomic pointers, head and tail. Each node contains a payload field of configurable size and a next pointer. Initialization allocates a sentinel node and sets both pointers to reference it. The queue operates on a circular structure with unbounded capacity, expanding by node allocation on demand. In-queue operations proceed by allocating a new node, writing the payload to its data field, and atomically swapping the tail pointer to reference the new node. The compare and swap instruction ensures atomicity without blocking. If the swap fails due to concurrent modification, the operation retries immediately. Payload size is validated at compiled time against the configured maximum. Failed allocations return an error code rather than blocking the caller. Dequeue operations first check if the queue is empty by comparing head and tail pointers. If empty, the operation returns immediately with a status code. Non-empty dequeues load the head pointer, read the next field of the sentinel node, and atomically advance the head. The old sentinel becomes the new head. The payload is copied to the caller's buffer before node deallocation occurs in a separate cleanup phase. Memory ordering semantics are enforced through acquire and release operations on pointer updates. In-queue uses release semantics when storing the tail pointer, ensuring payload writes propagate before the pointer becomes visible to readers. Dequeue uses acquire semantics when loading the head pointer. This ordering prevents reads from observing partially written payloads across threads operating on different processor cores. The ABA problem is mitigated through node reuse avoidance during the allocation phase. Nodes are allocated from a global memory pool and immediately marked with a generation counter. Pointer comparisons include both address and generation fields. When a dequeue advances the head pointer, the old node's generation increments. This prevents accidental reuse of recycled memory addresses from being confused with original allocations. Contention management is implemented through exponential backoff and retry loops. When a compare and swap fails, the thread spins for a duration proportional to 2 raised to the retry count, up to a configurable maximum. The backoff duration prevents tight spinning and reduces memory bus contention. This adaptive mechanism reduces latency when contention is low and improves throughput when multiple threads compete. Payload size restrictions are enforced through compile time constants. The maximum payload size is defined as queue node payload size bytes, defaulting to 256 bytes. Larger payloads require multiple allocations or external pointer indirection. The queue validates size parameters at initialization and returns failure codes for oversized write attempts. Padding is automatically inserted to maintain cache line alignment on supported architectures. Empty queue behavior is defined strictly. When tail and head pointers reference the same node and that node is the sentinel, no elements exist in the queue. Dequeue operations on empty queues return immediately with a specific error enumeration value rather than blocking. This non-blocking semantics allows callers to implement their own waiting strategies or retry logic at a higher level of abstraction. Overflow conditions do not apply to this implementation, as the queue expands dynamically by allocating new nodes. However, system memory exhaustion may prevent allocation. In this scenario, the in-queue operation returns an error code indicating allocation failure. The queue remains consistent and does not corrupt state. Subsequent operations continue normally if memory becomes available or if the queue is drained below the memory limit. Thread safety guarantees are achieved without locks through careful ordering and atomic operations. Multiple threads may in-queue and dequeue simultaneously. The implementation is obstruction-free. Any thread making progress blocks no other threads indefinitely. However, true lock-free behavior is not guaranteed under extreme contention due to the backoff mechanism, which may cause fairness delays in heavily contested scenarios. Node cleanup is performed asynchronously by a background reclamation thread that awakens periodically. Dequeued nodes are added to a pending deletion list and marked with a timestamp. The reclamation thread waits until all processor caches have synchronized before deallocating nodes. This hazard pointer-free approach trades cleanup latency for simplicity. Memory overhead grows with queue depth, but remains bounded by active allocation limits. Priority semantics are not implemented in the base queue. All in-queued items are processed in strict FIFO order. Attempts to assign priority to individual payloads are ignored. Applications requiring priority-based processing must implement prioritization at a higher layer using multiple queue instances or external ordering structures. The queue itself maintains no knowledge of payload content or semantics. Statistics collection is optional and controlled by a compile time flag. When enabled, atomic counters track in-queue attempts, successful in-queues, dequeue attempts, and successful dequeues. Retry counts are accumulated separately. These counters are updated using non-blocking atomic increment operations. Querying statistics returns snapshots, but not locked-in views, so counts may be slightly inconsistent across multiple counters due to concurrent updates. Fairness is approximated through the back-off mechanism, but not formally guaranteed. Threads encountering high contention experience exponentially increasing delays, allowing lower contention threads to progress. Starvation is not possible indefinitely because each failed operation increases back-off duration, eventually allowing retries to succeed. In very high contention scenarios, latency variance increases substantially, but throughput remains bounded by system resources. Debug mode enables additional validation and state checking. When compiled with debug queue enabled, each operation performs consistency checks on pointer fields and validates that node structures remain intact. A global invariant asserts that the sentinel node always exists and both head and tail point through valid nodes. These checks add significant overhead and are disabled in production builds by default. Integration examples show typical usage patterns. A sender thread calls in queue with a buffer and size parameter, checking the return status code. A receiver thread calls dequeue in a loop, handling empty queue returns by implementing external waiting logic. Multiple threads may be active simultaneously. The queue requires no initialization beyond a single create call and no explicit shutdown, returning resources automatically when the queue is destroyed.